This video introduces the hyperbolic identities and uses them to solve equations. Many of the hyperbolic identities are similar to the trig identities that you met in your A-level maths. Some differ, and we have Osborne's rule to help us identify which those are. So you'll see that we've got two that look almost familiar. This one being very similar to sine squared plus cos squared equals 1, and this one very similar to tan equals sine over cos. Osborne's rule states that we can take a trig identity, replace cos with cosh, sine with shine, and any product of two signs, so a sine squared with shine squared and a minus sign. It may also be that the sine squared is hidden, for example, in tan squared, and that would also gain a minus sign. So we can use our identities from A2. We can adjust them, as you can see here, has been done for the addition formulae, where we have a sine squared, it becomes a shine squared, and the sign is changed. So, having a look at question 1, we're going to use the definitions to prove two identities, both of which are quite algebraic, using exponentials, and then we're going to go on and use identities that we have converted from standard trig to solve equations. So, I've written these ones out already. Part A, the right-hand side, I have replaced cosh and shine with the exponential versions. We then expand both brackets, which gives us these two brackets here. We then collect the like terms and use our laws of indices to combine e to the a, e to the b, to the e to the a plus b, and likewise we have e to the minus a and e to the minus b. Combining those, we are able to have the one term. We can then write that over 2 and recognise that that is hyperbolic cos of a plus b, which is our left-hand side of the identity. Part B. Again, I replace hyperbolic cos and sine with their exponential versions. I expand the brackets and simplify. Here, all the exponential terms cancel, leaving me with the two constants, which sum to give me 1, which is my right-hand side. So question 1 has used the exponential definitions of the hyperbolics to prove the hyperbolic identities. Let's move on to using some identities. So, question 2 gives me a value for shine of a as 6 over 7, and I'm going to be asked to come up with cosh of a, tan of a, and shine of 2a. So, asked to find cosh of a. So cosh of a squared will be 6 over 7 squared, deducted from it, and that will equal 1 using the identity. This one is given to you in the formula book, so I can use it directly. That means that cosh squared of a, with some rearranging and simplifying, is 85 over 49, and therefore cosh 2a is the square root of 85 over 7. Now, just think about that carefully and think about the graph. We know that cosh of a will be greater than or equal to 1. Think about my cosh graph. Therefore, I only need the positive square root. Secondly, I'm being asked to find tangent of a, so I'm going to use my hyperbolic sine over hyperbolic cos identity. That means that we have 6 over 7 divided by root 85 over 7, which simplifies to 6 over root 85. And then last but not least, I'm being asked to find hyperbolic sine of 2a. So again, I'm going to use an identity. It is very similar to the trig identity because there are no squared sine terms involved. So I'm going to have 2 times the 6 over 7 times by the root 85 over 7, which simplifies to 12 root 85 over 49. Okay. So that's using 3 trig identities, one of which has a minus sign involved because we have a sine squared term which converts to a sine squared with a minus. Number 3. Now, when you first look at that, you think, oh, that's going to be my r cos x plus alpha method. And I could use that, but the working tends to be quite long and involved. So in this situation, I'm going to use the definitions to help me solve. And that is always a valid method. We could go back to using exponentials to help us solve trig. So let's have a look at this one. We've got 6 times by e to the x minus e to the minus x over 2 minus 2 times e to the x plus e to the minus x over 2, and that equals 7. So I'm going to expand the brackets. That will give me 3e to the x minus 3e to the minus x minus e to the x minus e to the minus x equals 7. Collecting like terms, I will get 2e to the x minus 4e to the minus x equals 7. I need to deal with the e to the minus x by multiplying the equation through by e to the x, so that will give me 2e to the 2x minus 4 equals 7e to the x. So I have a quadratic in e to the x. This one I can factorize and solve, so that gives me 2e to the x minus 1 and e to the x minus 4, which gives me e to the x equals, oh sorry, that's a plus, minus a half, solution there, and e to the x equals 4. Thinking about the graph, we will have no solution here, therefore x is going to be the log of 4. So there I've used the definition of the hyperbolics in order to be able to solve. Let's now have a look at number 4. If I was solving a similar trig equation, I would replace the cosine with the identity. I'm going to proceed in the similar way for this hyperbolic equation. So we want 1, and it's sine squared of x. Because it's a squared sine term, that means that I am going to need a plus here because I have a change of sign when I move from the trig identities. So expanding, that will give me 2 sine squared of x plus sine of x minus 1 equals 0. I am then in a position to factorise, so that gives me 2 sine x minus 1 and sine x plus 1. So that means that sine x equals a half and sine of x equals minus 1. And that means that x will be arc sine of a half, and x will be r sine of minus 1. I can now go straight to my formula book and use the logarithmic definitions of the inverses. So that's going to give me log of a half plus square root of a half squared plus 1, which is log of a half plus root 5 over 2. And in a similar way, x is the log of root 2 minus 1. And there I have my 2 solutions. One more thing where I would like you to add a note, please, onto the page. I'd like you to add a note that says to review example 15. Because example 15 solves a cosh x equation. And we need to be careful to ensure that we include 2 solutions for cosh x equals some value where the k is greater than 1, because we have to remember that the graph will have 2 solutions when any value of y is greater than 1. So have a look at example 15 and make sure that makes sense. I appreciate that we restrict the graph when we are defining a function, but when we are solving an equation, we need to consider all the possible solutions.